When your blockchain becomes critical national or enterprise infrastructure, best effort security isn't enough. In this module, we'll turn a conceptual trust layer into a hardened platform, securing nodes, keys, networks, and monitoring, so it can withstand real attackers, real outages, and real audits. Moving to shared blockchain-based trust also creates shared risk. A weakness in one participant's node, key management, or processes can damage the credibility of the entire network, even if the protocol itself is solid. So the design goal isn't just don't get hacked, but limit the blast radius. We'll think in layers: infrastructure, network, application, and governance, so a failure in one place doesn't turn into a systemic incident. Adding blockchain to an enterprise or government stack doesn't replace old threats, it stacks new ones on top. Traditional risks, node compromise, DDoS, and supply chain attacks still apply to every blockchain node, its OS, and its dependencies. On top of that, the trust layer itself becomes a target. Adversaries can try to influence consensus, corrupt shared state, or exploit flaws in smart contract logic. Across both worlds, insider risk is often the most dangerous pattern. Privileged administrators or operators who can abuse roles in a system that others assume is trustless. At the first security layer, design your network in clear zones with strict boundaries. Validators should never sit directly on the public internet. Expose only what you must through a DMZ, and keep validator nodes in a protected segment reachable only over tightly controlled paths. All node-to-node traffic should be mutually authenticated and encrypted, typically with MTLS, so connections are both private and strongly identified. Run firewalls in a default deny, whitelist-only model, so only explicitly approved peers and ports are reachable. For cross-organization connectivity, use VPN or MPLS links, so consortium traffic doesn't depend on raw, unauthenticated internet paths. Hardening blockchain nodes is about removing easy win conditions for attackers. Start by shrinking the attack surface. Use a hardened OS image, apply CIS benchmarks, and disable any service that consensus doesn't genuinely need. Then treat every node's configuration as code. Tools like Ansible or Terraform keep instances consistent and let you detect and roll back drift quickly. Run the node under tightly scoped service accounts, never as root, and separate duties between operations and administration. Finally, patch aggressively but predictably, using automated staggered patch cycles so you stay secure without destabilizing consensus. Here we anchor trust directly in hardware. Hardware security modules are tamper-resistant devices that generate and protect signing keys so they can't be copied or exfiltrated through software attacks. Secure enclaves, like Intel SGX or ARM Trust Zone, isolate sensitive computations even if the main operating system is compromised. Secure boot ensures the machine only starts with trusted firmware and code. Together, these guarantees mean critical keys effectively never leave hardened hardware. In blockchain-based trust infrastructure, keys are the real root of trust, so their lifecycle matters more than any individual algorithm. Begin with generation. Use strong, verifiable entropy and FIP's validated modules so you can defend your keys in audits and, if needed, in court. Next is storage. Private keys belong in HSMs or cloud KMS services and should never appear in plain text outside tightly controlled boundaries or memory. Rotation limits blast radius. Automate it and tie rotations to events like role changes, key aging, or suspected compromise. Finally, revocation has to propagate quickly across all organizations, with CRLs or OCSP built into every policy decision point. Governance and access control for a blockchain trust platform. Start with role-based access control or RBAC access control, or RBAC. Every human and system identity gets a clearly defined role, not a blanket admin. Least privilege means operators, developers, and auditors see only what they need. God mode accounts are eliminated. Strong authentication, such as MFA and hardware tokens, protects powerful roles. For particularly sensitive operations, use just-in-time elevation, so high-risk access is temporary, tightly approved, and fully auditable. Separation of duties becomes your human firewall. Design capabilities so that no single role can do everything end-to-end. Operations teams manage the infrastructure. They can patch, reboot, and monitor nodes, but they never hold keys and cannot sign transactions. A rogue admin can't forge history. Developers write and test smart contracts, but they cannot unilaterally deploy them into production. That gap forces review, testing, and change control. Business users initiate workflows and approve business actions, but they never touch the underlying OS or cryptographic material. On top of that, dual control means any critical upgrade or governance action requires multiple independent parties to approve, making both collusion and simple mistakes much harder. Monitoring is where your blockchain stops being a lab project and becomes real infrastructure. Security operations need visibility not only into the OS, but also into nodes, smart contracts, and HSMs as a unified signal set. That's why SIM integration is essential. All logs and alerts land in one place. From there, anomaly detection can flag suspicious behavior or configuration drift. And federated alerting gives every consortium member shared, near real-time visibility into what matters. When something goes wrong in a blockchain trust infrastructure, the first question is, did we lose a node or did we lose keys? For a suspected node compromise, containment comes first. Isolate that node from the network, revoke any certificates it used to participate, and only rejoin after you've rebuilt and validated its environment. For a key compromise, the timeline is even tighter. Immediately revoke affected credentials, rotate key material across dependent systems, and update trust anchors so every party agrees on which keys remain valid. In both scenarios, preserve evidence. Snapshot logs, configurations, and relevant ledger state for forensic analysis and post-incident reviews. When a smart contract is part of critical infrastructure, you assume something will eventually go wrong and design for that from the start. Begin with proactive analysis, rigorous code review, static and dynamic analysis, and continuous on-chain monitoring with clear alert thresholds. Then add a circuit breaker, an emergency pause that can stop new interactions while preserving state. Combine that with a well-governed upgrade path, typically via proxy contracts, so you can patch logic without rewriting history. Finally, script your communications plan so affected organizations and users receive fast, consistent guidance. A secure architecture blueprint is less about a single diagram and more about three enduring habits. First, defense in depth. Assume individual controls will fail, and layer protections from hardware and keys up through the node, the network, and governance. Second, rely on reference architectures that have actually been tested and validated rather than inventing everything from scratch. Third, invest in continuous assurance through red teaming and regular tabletop exercises, so you keep learning where your design bends and where it breaks. Let's pause for a moment. We've focused on how to secure nodes, keys, and the underlying infrastructure. Next, we'll zoom out to the rules around them: compliance, legal obligations, and policy. Think of the shift as moving from can attackers break it to can auditors and regulators trust it.